I am very happy this week to be hosting my friend Dr. Molly Patterson from Binghamton University. Molly got her bachelor's in geology from Colgate, then a master's in geology at Southern Illinois University, where she worked on andrill cores. And then she got her PhD in geology from Victoria University of Wellington, which is in New Zealand, which is sick. And then she did a postdoc at UMass Amherst, which is even more sick. And that's where I met her. There's several of us in this room that are UMass alums, and I first met Molly at that. And then she got a job at what was at the time SUNY Binghamton, and they dropped the SUNY a while ago. Yeah. But around that time, she came down to UTIG. We had an IODP workshop that we were just reminiscing about back in 2017 about demystifying the proposal process for early career scientists. That was in this room with a bunch of people who have since gone on to do a lot of IODP stuff, future staff scientists and things like that. She's currently an associate professor at the University of Binghamton. And she's also this year an IODP ocean discovery lecturer. And so that's what her talk is going to be broadly focused on today. So without further ado, Dr. Molly Patterson.
Thanks for inviting me. When I got my list of kind of talk assignments, I was super excited to see this was on the agenda because of all the names and people in the room and familiar faces. And I was also really honored to be asked because I feel like I've really benefited a lot from the ocean drilling community. And it's a community I'm really proud to be a part of. So for the science part of this talk, I'm going to talk a little bit about a record that I worked on during my PhD, and then another record that a recent master's student of mine developed. And we've been trying to tease these records together to paint a picture or tell a story about how different parts or different margins of the Antarctic ice sheet have kind of varied maybe throughout the Pliocene. And thank you. So I'm going to talk about the relevance of these ocean drilling records in the context kind of some of the land or ice-based drilling efforts that have also gone on regionally over the last few years related to the andrill record, but also kind of highlight how this fits into what we're trying to do with the Suez 2C project along the Cycle Coast margin. So these talks are a little different from my experience of witnessing them. So I'm going to talk a little bit about my science journey and how I've been a part of ocean and land-based drilling projects. I'm going to talk a little bit about the opportunities through IODP, especially focusing on some of the stuff that I've really benefited from as an early career researcher. And then I'm going to talk a little bit about science. So my science journey really started following my freshman year. I used my first passion in life to kind of finance that journey to figure out what I wanted to be when I grew up. And I took an oceanography course, and Amy Leventer taught that course. And she gave a lecture during one of the classes about her research and how it fit in with the topics that we were learning about in class. And Amy has spent her career going down on icebreakers and coring into the seafloor in the Southern Ocean. And it was the first time it really kind of dawned on me that maybe I could do science because I can identify shapes and I can count. But I also thought it was really cool that people get to do this. And so I worked 3 summers doing research in her lab, and then she kind of handed me off to Scott Ishman at SIU Carbondale. And at the time, Scott was a part of this project called Andrill. It was a land-based drilling project. And I kind of pivoted from looking at diatoms to looking at foraminifera. But this also was the first time I met one of the co-chief scientists, a part of that project, Dr. Dave Harwood, who's been a tremendous mentor to me over the last 10 years and trying to develop the Suez 2C project. But Scott gave me some really good advice at the end of my master's because I really loved working on this project. And he said, if you're really serious about maybe continuing on this way, I would consider doing a PhD abroad because it's a really nice natural way to build international collaborations. These projects are really expensive. They're logistically hard to do, and they require a lot of international cooperation. So that's what really motivated me to go to New Zealand. And I worked with another one of the co-chief scientists, part of that project, Tim Naish, but I really worked with this postdoc at the time, Rob Mackay. And it was an awesome experience. Rob had just sailed on an expedition, so I got to work on some recent material that was just recovered from the Wilkes Land margin, which I'm going to talk about today. But then I also worked on records, archive records that were recovered, 10 years beforehand from the Southwest Pacific. And then I got to kind of climb around on outcrop records in Wanganui Basin in New Zealand to develop a project to help promote a drilling project that evolved into trying to develop a sea level record. So really thinking about how the ice margin varies, how it influences deep ocean circulation into the Pacific, but also how does sea level vary across during the Pliocene. This is also the first time I sailed on an expedition. And this was an awesome experience because a lot of the scientific objectives couldn't be met because of the challenges that we faced with sea ice. And it really gave me that appreciation of how difficult it is to work in the Southern Ocean and Antarctica specifically. At the end of my PhD, I was really sick of Antarctica, believe it or not, but not that sick of it. I kept hearing these talks about this Lake Elgagackin project. And so I was lucky, I got a postdoc with the Lakey group and trying to think about how these really warm events they were observing in this lake record in the Arctic related to these really warm events that were observed in some of the Anvil records. But this also introduced me to the International Continental Science Drilling Program for the first time. So kind of the equivalent program to ocean drilling, and which I'll talk more about in a bit. But Julie gave me some really great advice. It was at the end of my postdoc, I gave my first talk on what has helped evolve into the Swayze 2C project. And she told me to, it's always good to have a big project that you're working on in the long term with other small projects that you can help kind of mentor graduate students. But it's always really good to have something in the background to work for. I got my job at Binghamton in 2016. We have a faculty of about 8. We've been hiring the last couple of years. We're a small group of people who focus on paleoclimate, but I like to think we're small and mighty because we cover different regions, we cover different topics, we cover different techniques, and I think it provides a pretty nice opportunity for our graduate students of having these different perspectives on paleoclimate questions. So a lot of my work has been focused on looking at marine records and kind of these ice marginal records in the Southwest Pacific and the Ross Sea region, but also teasing away at these records up in the North Pacific. But recently, in the last couple of years, I have a PhD student who got the opportunity to sail on an expedition in the North Atlantic. So she's really kind of forcing me to think about the North Atlantic. But this, professionally, this has probably been one of the most gratifying parts of my career since, watching a student go and sail and then seeing all these collaborations and projects and developing their own ideas. It's been a really awesome thing to watch as I've been mentoring students. All right, so the International Ocean Discovery Program and some of the opportunities. I know a lot of you are familiar with this program, right? It's an international marine research collaboration that explores Earth's history using different platforms to access seafloor samples and to monitor the seafloor. It has a pretty awesome history. And in that it started with people wanting to do something really extreme and recover material from the crust mantle boundary. And that ended up being a failure. But what happened was the scientific community, pivoted and saw other opportunities. And that evolved into these, multiple phases of the ocean drilling program, starting with DSDP in the 1970s. So it's a program that, people had an idea, extreme idea, they failed. People saw opportunities in other ways. People have carried that program on in the past, and they're going to carry it on in the future. And this is probably one of the most kind of iconic figures, of ocean drilling, where it highlights all of these, basically, I think of them as achievements that stem from an original failure, or that have provided material that have really helped us understand better Earth system processes through time. So a really remarkable map that shows a lot of success, but it really started from a failure. And it wasn't until about 60 years later that that original goal was achieved. So science takes time. You can fail, but there's still opportunities, and you can make opportunities out of those failures. I personally think, and I'm 100% biased on it, and this relates to my talk, but also one of the great achievements, right, of ocean drilling is it's helped paint a picture of where we're headed in the future. These drilling platforms, they can access deeper, older material, right? And I just want to highlight one of those time periods, the mid-Pliocene warm period. A lot of these records have really highlighted, right, that this is the last period in Earth's history where atmospheric CO2 temperatures were above 400 parts per million and global mean temperatures exceeded 2 degrees Celsius. But also what's really interesting about this is the range of sea level estimates that for the mid-Pliocene, right? You have boundary conditions to where we're headed, where we're going, but a big range in terms of what the ice margins are actually doing during that period of time. So IODP, right, is now in this IODP phase, and the foundation of this program is built on mission-specific platforms, drilling platforms that can go into different regions and access different unique records based on different platforms. And one of my hopes with the Space2C project is that we can provide another tool that's proven to use for accessing some of these remote high latitude regions to address important science questions. So each of those expeditions, right, they fall on, they have to meet some strategic objective. Obviously, you might want to meet more than one, but as from a student perspective, these are really great documents, right? Because it's a really great place to go for literature and to understand what are some of the important questions the international science community is wanting to address. But another part of this is that, for each of these expeditions, right, they have to meet these strategic objectives, but there are longer term research efforts that are associated with these flagship initiatives that take much longer time to develop, 10 to 20 years. And they might require looking at multiple records within a given region, whether they're just ocean records or a combination of ocean and land-based drilling efforts. And I'll talk more about, I'll give an example of one of these flagship initiatives a little bit later. Right, all these materials that have been recovered through the program are stored at repositories. Anybody can go and access them. And there's the three main ones, right? The one in Texas, the one in Germany, and the one in Japan. And one thing that, I keep telling everybody, because I just learned this, is if you are interested in really interesting science questions in the Indian Ocean and the Western Pacific, a really cheap way, if you don't have a lot of funding, to get some data is there actually scanned cores for you that already exist in their repository, and you can use them, right, for developing proposals or mentoring undergrads or more master's theses. I think one of the best ways to get involved in IODP is to attend workshops. I've met a lot of friends through attending these workshops. I've met a lot of colleagues at various career stages. I attended one of these workshops that happened in Texas A&M before a whole bunch of expeditions to the Southern Ocean. I had one conversation with Dave Harwood, and it really set me on a path for the next 10 years that I wouldn't have never in a million years thought I'd be doing. You can attend workshops. With every workshops, there's a report. And so we can't attend them, but it's a summary report where you can still kind of stay up to date. And one of my favorite workshops, I don't attend a lot of workshops. I have two little kids. But I went to this one last March. It was on the future of U.S. marine seafloor and subsea floor sampling. It was an awesome workshop, super positive. There was all these talks about all the resources within the U.S. that are accessible to go and write a proposal and recover material. And it really highlighted to me that beyond IODP, right, it's a really good time to better understand just our national capabilities within the UNOLS program and within the UNOLS fleet. And you don't necessarily have to write a proposal, right, to use these systems. They have workshops for early career people. There's bursts that are sometimes available for students or faculty members to apply to sail on. But and it's not just about the science, right? There's like these marine technician internship programs that are also available. And I say that because a lot of the building blocks for IODP expeditions that have happened stem from these coring expeditions, right? Short coring expeditions, for example, provided the first direct evidence to quantitatively test Milankovich's hypothesis that we might now take for granted, right? Where you have the waxing and waning of ice sheets in response to that natural forcing of Earth's orbital geometry just changing around the sun. Where you have those extremes in Earth's axial tilt that really modulate changes in mean annual insolation, whereas that change in the elliptical geometry around the sun really intensify the summer melt seasons in polar regions. But it has been ocean drilling that's been able to go back farther in time and paint that picture farther back in time and how the climate has varied. I'm going to highlight just that record of the last 5 million years here, because when you compare, right, those extremes in climate as represented from kind of these classic paleoceanographic records that are recovered from all these different ocean basins, typically not from ice margins, it really highlights that the Pliocene is a period of time when ice volume was smaller than modern. And it really isn't until you get this big cooling event around 3.3 million years ago, around marine isotope stage M2, that kickstarts the system into building ice volume in both polar regions, but also the variability in the climate system changes around 1 million years. You go from a system that's really dominated by 40,000 year variability to a system that's really dominated by 100,000 year variability in response to that natural forcing. So one of the questions I've been really interested in is stemming back from my PhD days to even now, is what does this variability actually mean in terms of ice volume? What volume of ice is actually changing? Is it northern hemisphere? Is it sectors of Antarctica? Is it Antarctica as a whole? And what are the natural forcing factors that are driving those past ice volume changes that are represented in this curve? So really trying to get at past ice dynamics. All right, so now I'm going to talk about how I've been trying to address this from using ocean records. So the two records I'm going to talk about come from two different IODP expeditions that have 8 years, that were sailed 8 years apart from each other, right? The one is from this Wilkes Land margin. The other one is just around the corner over here in the Ross Sea margin. So they look spatially far apart. Temporally, the time at which they were recovered is also, almost a decade. But the reality is they were all motivated. These expeditions were all motivated by initiatives back in the 1970s as part of that initial phase of ocean drilling, where DSDP leg 28, left port from Australia, sailed down to the Wilkes Land margin, recovered material, sailed over to the Ross Sea, and then back to Littleton, New Zealand. And this was a pretty important expedition. It laid a foundation and how we think about the paleoclimate history of Antarctica, right? It provided some of that first evidence of glaciation prior to the early Miocene. It also provided evidence that the Pliocene Antarctic ice sheet was really dynamic. And it also provided some of the initial observations as Antarctica migrated away to the high southern latitudes that hypothesis about thermal isolation, and improved some of the Southern Ocean biostratigraphy, and it also kind of paved the way for some of these ideas on the interaction between ice loading and tectonics. And something that, a lot of effort back in the 1970s to get down there. And people on the ship had the foresight to realize that it would take a really long time to get back to the Ross Sea. And their response to that was to develop these international consortiums to drill below the ice shelf and the sea ice in different regions, primarily within the McMurdo Sound region, because there's two main bases there, the US station and the New Zealand station, which allow to support these operations in terms of logistical support. And they've mostly been led by the US and the New Zealanders for that reason. And they've really provided these nice snapshot records where all these black rectangles highlight the time intervals where there's geological records that are recovered from these different land-based drilling programs. And they've been trying to tie that, the community has been trying to tie them into those or connect them with those ocean-based records, and then also relate them to some of those more distal paleoceanographic records that we use to try to interpret Cenozoic climate change. So they're not continuous, but they provide really important snapshots of the history of the ice sheet. The most recent project was Andrel, right? And Andrel, I think two of the main big impacts of Andrel was it pretty much ground truth in some parts of that 5 million year record that Antarctica varied at that 40,000 year variability because of the really exceptionally well preserved. I know this is a strat column. The last summer I went down to the Oregon State Repository and looked at these sections, and these are beautiful. People are interested in this. I highly recommend to use that repository and look at them. But it was these awesome sequences of diamictite overlaid by mudstones and diatomite, right? And so they're the direct observations of the ice margin advancing and retreating in response to that natural forcing. Andrel was really awesome too, in that it really demonstrated the utility of combining geological records with ice sheet models. And the people who really led the way of that is Rob DeConto and Dave Fuller, because it's really hard, it's really expensive to get these records, and to really extrapolate those results in a meaningful way in terms of the full continent. These ice sheet modeling experiments are really important. And at times they help motivate where to go and drill records. So since Andrel, there's also been other land-based drilling projects. I'm just going to highlight this one from the North Island, New Zealand, and Wanganui, because I'm completely biased. But more records, and when you start to compare more records, typically you start to see how the variability in one record isn't consistent with the variability in all these different records, whether it's an ice sheet model, whether it's real classic paleoceanographic data sets versus these independent sea level records. And what this New Zealand record really highlighted was that the variability in sea level, these independent sea level records, was different from the geochemical proxies in ice sheet modeling, which is really kind of motivated, kind of putting together teasing together a story of trying to better understand the natural forcing of ice sheets and trying to tease apart the story of where these signals are coming from. So the first record I'm going to talk about is from this Expedition 318 from the Wilkes Land margin. It sits on the continental rise. It was a really unique site. It wasn't even a primary site. The reason why they drilled this site is because they kept getting chased off the ice margin. But it was one of the first more continuous records from the ice margin during the Pliocene. And it's probably had the most papers come out of any of the other sites that were drilled for the expedition. But I'm just trying to highlight here also the decades worth of work that by individual PI-based expeditions and studies from those smaller coring expeditions really fed and provided the motivation to go back to that Wilkes Land margin. So this is a study that came from my PhD, and basically the guts of it is that I worked on this record. I did a lot of grain size work from this record that extends from 4.2 to about 2 million years ago. And so within that record, we kind of capture that big cooling event, but across that cooling event, you have this change in the variability of this iceberg rafted debris record, or icebergs breaking off the margin and you know, melting sand and getting deposited at that site. And across that cooling event, you have this switch in terms of variability. And so we kind of related this to, we thought about this also in terms of what the diatoms are doing around the margin. There's this evolutionary shift where you have these more warmer species compared to these colder species that are more sea ice tolerant. So we related the switch into natural forcing to related to regime changes and cooling along the margin and the development of a perennial sea ice field. So sea ice that sticks around for multiple summer melt seasons. And combining with some of the geochemical provenance data really kind of highlighted that these icebergs were really breaking off the margin during deglaciation events. So they were, the ice margin retreats, you get these big armadas, and then it retreats inland. But I did that, and I then had the opportunity to sail on Expedition 374 with your very own Benjamin Kiesling. This was an awesome expedition to be a part of. And I'm just going to highlight one thing here is that, you know, the people who sailed on that original DSDP leg, their foresight was really right, because this was, as the legend goes, this was one of the longest standing proposals in IODP history. It started with Peter back in the 1980s, and it kept getting handed off, and it kept getting, or handed off in advance to different scientists. And then it finally went in 2018. And this was really kind of an awesome experience, because at this time, my one PhD advisor had abandoned me at like the last month of my PhD to work on this. But it was really awesome to see Rob at that time go from postdoc to lecturer working on such a big project. But so also this margin was a really an awesome expedition to be a sedimentologist on, because we drilled on the shelf, we drilled on the slope, we drilled on the rise, and there was a lot of variability. And there's in terms of the different types of sediment archives that you saw, but this also margin, you know, there's really cold dense waters that form on the shelf that cascade down these submarine canyons. You have the Antarctic slope current that's winnowing sediment, and you get these beautiful chondrite sequences. And you also in this region, this is also where circumpolar deep water, relatively warmer water gets up onto the shelf in the modern. So oceanographically, it's also a really interesting place to ask questions about ice sheet ocean interactions. And the site U1524 that I'm going to talk about, really analogous to that Wilkes-Land site. It's, you know, on the levee of a submarine channel that's just where bottom water is flowing out of, and it's really being built up by that overflow of sediment onto the bank. This is a record following kind of that same workflow that I did for my PhD, that my master's student did, you know, developing a grain size record. And when we plotted this up the first time, it was like, wow, okay, there's variability. This actually looks way better than the record I've worked on from Wilkes-Land. And it is a little bit maybe even more interesting, and that you have this period. So this doesn't temporally necessarily overlap with that whole Wilkes-Land record, but at the base of it is that really cold event, that marine isotope stage M2 event. And what it really highlights is that you get these kind of pulsing events, we think, that are you know, just more frequent, may be analogous to more of an ice margin that looks like that, whereas it isn't until kind of around 2.8 million years ago, then you get these big iceberg events that have this really beautiful cyclicity to it. And a colleague of mine got me thinking about this idea where these might represent, these big pulses might represent really big disintegration events of the ice margin. So going from an ice margin that doesn't maybe necessarily have a sustained ice shelf to an ice margin that is sustaining ice shelves, but those ice shelves are breaking up and creating these iceberg armada events. So because this is kind of a site that's really analogous to kind of your classic paleoceanography sites in terms of continuous deposition, we can do some fancy statistics and try to tease out to see what type of, are there any orbital frequencies embedded within these records? And it's pretty interesting in that, you know, similar to the Wilkes-Land margin, you see, you know, there's not one signal that's dominating it, but that there's, you know, this pretty significant 40,000 year pacing in the bottom part of that record, where you have these kind of more continuous low amplitude events. And then as you get into the earlier part of the record, that 100,000 year signal is really dominant, but there is that 100,000 year signal pretty much throughout the record. So when Christiana showed me this, I was like, oh, how are we going to make sense of this? We have two records right next to each other. They have different variabilities. And I found myself just staring at what really this figure stems from, is an animation that was done by an education outreach officer, part of the Scotia Sea expedition up here. And it highlights these different ice margins with different colors, represent the source areas of these different dots, which are the icebergs that are breaking off that margin. And in the Ross Sea, you have this nice gyre system. So these bergs that break off of West Antarctica in the Ross Ice Shelf rarely get over to this Wilkes-Land margin, because that gyre makes them flow north. So there are two sites next to each other, but those currents might have something in terms of where those bergs are actually going and where they make it. At the same time, Rob kind of pointed me in the direction of trying to think about, you know, from a modeling standpoint, there really is considerable spatial variability in the magnitude of future ice mass loss in these different catchments. And when you just kind of think about this West Antarctic catchment versus this Wilkes and Aurora basin catchments, they respond differently in these sensitivity tests. The Wilkes-Land margin, that first record I showed you in that area, really seems more sensitive to top-down melting or warming just from the atmosphere, whereas the West Antarctic catchments really seem more sensitive to warming from the ocean. And if you scale those processes up on geological time scales, that the warming from the atmosphere typically is associated with that direct insulation forcing from changes in eccentricity, whereas the obliquity-driven forcing and ocean dynamics driving the melting of this catchment here, which I'll explain more here in a minute. So from modern observations from satellites, we know that there's surface melt, right? It doesn't contribute to the ice mass loss today, but it plays a really important role in making these meltwater ponds and fracturing the ice and preconditioning it to make icebergs. Whereas the marine kind of melt influence kind of on geological times has been explained by, as you increase Earth's axial tilt, you're pushing those oceanic fronts and atmospheric zones farther southward, which allow for upwelling to happen of relatively warmer water, circumpolar deep water, onto the continental shelf and melting ice from the base up. So the kind of example here, right, is the obliquity-driven changes and driving these ocean dynamic changes versus top-down melting, really preconditioning the ice for breakup from surface melt. So now trying to kind of make sense of this. So in this lower part of the record from that M2 event, but within that mid-Pliocene warm period, so following a cooling event, but within a warm period, 2 degrees warmer than modern, highest atmospheric CO2 temperatures, less sea ice, that maybe this ice margin is more sensitive to some of that oceanic forcing, where you have a reduced sea ice field. Whereas once that sea ice field evolves in this region, the ice margin really becomes more sensitive relative to that marine part to surface melt within this record. This is how we've been trying to tease this out and make sense. And when you compare it to that Wilkes-Land record, that's really dominated, the whole record in this interval of time is really dominated by that 100,000 year variability. It kind of starts to make sense that just surface melt might actually play an important role in the sea level record I showed you earlier. But when we can, so there's always a 100,000 year signal there. There's a 40,000 year signal there, and trying to relate this now the observations from Andrel, these blue rectangles highlight intervals with temporal intervals within the Andrel record, where there's really clear 40,000 year cycles. And where we have that really strong 40,000 year signal in our record, it also correlates to this to the 40,000 year cycles in Andrel. So trying to make sense of these advances and retreats from direct observations of the ice margin, but also in terms of these ocean records. And where that 40,000 year signal disappears is where you start to see this change in the types of mud basically that's being deposited, where it's diatomite with less mud. And the hypothesis here is that once you get into about 2.8 million years ago, you really transition into this kind of more polar ice sheet that sustains ice shelves, which has been proposed separately from the Angel project. And it also coincides with the development of the sea ice field during that time. So this is the variability right in the oxygen isotope record, the LRO4 stack during that time. And I just embedded maybe our interpretations here, where this signal here, this 100,000 year embedded variability is really related to ice volume loss from east and west. And this 40,000 year variability might be related to West Antarctic ice mass loss. And then you have the evolution of the Northern Hemisphere ice sheets. And this kind of makes sense with these independent sea level records from New Zealand that really highlight that really have these really nice resolve and a precession and eccentricity dominated cycles to it. So in order to get these big amplitude changes in sea level during the Pliocene, right, you need ice mass loss from both catchment areas. But the mid-Pliocene is really interesting because during a time where you have less sea ice, that ocean feedback really kind of kicks in. So that's kind of what I've tried to do from ocean drilling records to tease out where ice volume is changing. And now I'm going to talk about efforts to build off of that Andrel effort, these ocean drilling efforts, and trying to get those direct records to see how much the ice margin actually retreated. And this is where the Space 2C project stands for the sensitivity of the West Antarctic ice sheet to 2 degrees Celsius warming comes in. This is an international project. There's 10 different nations that are involved, and really Andrel has provided the blueprint to motivate this project. And it's been 15 years since Andrel, twice the duration that all those other projects that came before it, which were basically every 7 years. So what we're trying to do with the Space 2C project is we're trying to drill and access records along the Cycle coast margin. First at the CAM, just adjacent to the CAM ice stream, and then at Prairie Ice Rise. And the reason why, a lot of the reason why these sites were picked is because somebody like an ice sheet modeler, Rob DeCanto, put his finger on a map and said, I need more data here. And okay. But it also is adjacent to this traverse that supplies the South Pole Station. So logistically, you could get the equipment out to the sites. Prairie Ice Rise and KISS are, they're just adjacent to each other, but they're very different. Prairie Ice Rise is an area of the ice sheet where it's grounded, and it's actually buttressing and holding back the flow of the upstream ice. And there's really a good combination of modern glaciology, paleoglaciology, and geological questions that we're trying to address here. KISS, we've been trying to address these kind of ice shelf ocean feedbacks through geological time, but we've also been able to deploy moorings and have that are still collecting data. And it's also kind of a unique margin. The Amundsen Sea sector gets a lot of attention, right, because it's losing ice mass, but along the Cycle coast margin, you're actually gaining ice mass. But if you zoom in even further to these different ice streams, you see some are very active, some are very stagnant. And there's been some studies in the kind of recent to say that the stagnation of one ice stream might be related to the reactivation of another ice stream. But notably, the ice at these two sites is pretty stagnant, which is fundamental for our drilling system. So Space 2C kind of represents, in my mind, an unofficial flagship initiative. because it really builds off of, these different drilling platforms within a given region and trying to build this transect of sites that can tease in these oceanographic records with getting farther in interior records from West Antarctica. And I think the most exciting thing is, we have no idea what the age of the material is at these sites. And one of the, I think, big objectives that we have with the project is if we can just get some fundamental understanding of the underlying stratigraphy and have a proven technology, then maybe we can ask more questions to get more continuous records in some of the adjacent basins along this region. So this is what our camp setup looks like. This is our drill tent. This is the drilling system that was specifically designed for this project. It fits within the modern U.S. Antarctic program logistics, where you could put this in a plane, put it in the deep field, or you could traverse it out. This is basically the big tubs where they melt the water to melt the hole through the ice. Back here is Tent City, where all the scientists live. This blue little rectangle there, that's the porta potty. Marie asked me that. This is the rag tent back there. This is a heated science tent. This is a non-heated science tent. It's a lot of effort. It's about 15 days to check a bunch of this equipment out to site. And when we're at site for about a month. We've had some challenges with the drilling system, but I'm very confident based on the last few months and work being done by the engineers and drillers that we'll be successful next year. We've taken a lot of gravity cores along at the KISS site. We have collected some oceanographic observations. We have long-term monitoring observations. We know we can piston core the sediment, which is really heartbreaking in some ways. And we can already address 2 of our 5 objectives, addressing Holocene ice dynamic questions at this site, but also a ton of microbiology and ancient DNA work that's being done to hopefully address some of those other objectives that get at Pleistocene and Pliocene ice dynamics. The next site that we're going to is Prairie Ice Rise. And, there's Prairie Lab and McMurdo Station, there's Prairie Ice Rise. And I had to give this talk this last year about why are we going to Prairie Ice Rise? And I was like, I got to figure out who this is named after. And so it's named after Albert Prairie. And I read his obituary. I read a bunch of this. I read part of this publication he wrote when he was at NSF. It was called The Long Look Ahead. And it turns out Albert Prairie, I'm his biggest fan right now. This guy led a tremendous life. He is the reason why biological sciences, cartography, geology, it is all kind of now happening in Antarctica. He advocated for this. He advocated for international cooperation and between countries, and to address, to really, for scientists to really participate in the solutions to problems, like things like sea level rise. And he really wanted to demonstrate the value of international science. He was a heavy influence on starting VSDP. He outfitted the Cannon for oceanographic research, and he even led some of those expeditions. I mean, this is a life well lived. And he's greatly admired by many of his colleagues, what I took away from all this. So all these records that we've recovered are going to be stored at a different facility, the Oregon State facility, and they'll be open to the science community after the moratorium. So this is the last slide. I do this for every talk for students. This is an interesting project. If this is an interesting project, you want to get involved. These are all the U.S. science team members. We have a website. We have a big international team. Lots of graduate student opportunities, postdoc opportunities. We have funding for another glacial sedimentology school that will be housed at Oregon State. We'll have a focus on subglacial lake sediments, androl stuff, but also thinking about those IODP records from both the Antarctic and the New Greenland records. So I'll leave it there and I'll open up for any questions.
Yeah, Molly, that was a great talk. Thank you. We have plenty of time for questions if anybody has any.
Thanks for fitting so much into such a small window of time. So I had this question before you put this slide up, which is what are ways that students can get involved? And this is a great introduction for Space to See. Do you have a sense for IODP cubed? What are the opportunities for student involvement?
Yeah, I should be better prepared for that. So I'm gonna go back to that slide. And I only know this because, so colleague at Binghamton, Adrian Lamb, is all over this. And that's why it's nice having a, I guess, colleague when you're just down the hall from you. Where is it? Sorry, look away so I don't make you nauseous. Okay. So my understanding is that these Spark proposals are proposals that you can submit to go to different repositories and access archive records and build projects. And this is kind of why I kind of highlight the flagship programs, right? Because there's all these existing records and there's also ICDP, right, that has projects. And if, you know, ICDP is already drilled in one region, you know, if you go and you look in the repository, maybe there's questions that you can ask that build off existing records. And, you know, could be an unofficial flagship type thing. So I think my understanding is these Spark proposals, which are more, Chris, you probably know this a little bit better, are for work at repositories, right? Yeah.
Yeah, and they have to be, so IODP 3 doesn't include the US right now, so it has to be led by IODP 3 scientists. But there is going to be a mechanism through NSF in the new I forget the acronym. There's the new Scientific Ocean Drilling Coordinating Office, and there's going to be with that an ODP program at NSF that we're not calling ODP anymore for reasons. SODCO is the office, but there's a program too. I was talking to Kevin Johnson about this the other day, and he gave me it's not SIP, it's something else. But they're going to fund this sort of work as well. And the U.S. Science Support Program, current U.S. Science Support Program, is getting rolled over into SODCO, and they are going to continue funding student. So that's what at Lamont, right? They're going to keep funding student participation in workshops and cruises of opportunity, things of that nature. NSF is working with IODP 3 to fund expedition. It says it doesn't. Oh yeah, 501. There we go. The New England Shelf Hydrology. And they will probably in the future also support U.S. participation in other things, but that is not worked out yet. But they probably will, and there will be U.S. drilling coming online soon. But there's already workshops. So I've just been encouraging my students to sign up. There's one in College Station this summer that's like core descriptions. There's another one in Bremen that there's U.S. funding to attend. That's I think it's polar stuff, isn't it? Do you know?
Yeah.
I don't know. Yeah.
There's so much.
There's a lot.
Yeah, and that's why I also buttons here. And I got advice from another speaker. There's this website here for updates to go to. Yeah.
Thank you for this talk. It's really awesome. And I like seeing the integration of like ice dynamics and extent and also relating that to core history. I'm interested in modeling the interaction between ice sheets and sediment, so the active sedimentation building process. And I want to make sure I'm understanding this right. So with the IBRD, there's a larger amplitude, so increase in rafted debris in the later Pliocene when we're shifting to a colder period. Right. And then we had smaller variability or lower amplitude of this rafted debris when it was slightly warmer.
And I think that there's like regional differences.
Okay. Okay, cool. So I guess my key takeaway from this should be even if we are in colder periods, we can expect an increase of sediment from ice moving, essentially.
From a marine record, if you were looking at like a continental rise record, um, it's funny. So within this record, even just like the muds, they actually have slower sedimentation rate, but you get during a glacial period, you get ice advance and more kind of terrigenous sediment being remobilized offshore, right? But you actually, during interglacials, you have high productivity during periods when the sedimentation rate is high because of the biological input. Does that answer your question?
Yeah, yeah, no, that helps. I think I'm just trying to think about the amount of sediment and where it's coming from. Like, are we like growing ice and that's why we have like an increase in sediment? So it's interesting, I think, not thinking about icebergs at least, but in terms of like iceberg rafted debris, that there's a ton of sediment still coming off of the ice sheet, even if we are advancing and disintegrating, yeah, ice shelves.
Right, and so the part of the annual record, I think that's interesting, I went to lab in my class on this, is how I know this off the top of my head, is in the Miocene part, the late Miocene part, is actually sed rates are really high, and you get these really thick mudstones, and it's because you have more meltwater, subglacial meltwater, that's contributing to higher sedimentation loads, whereas as the ice margin cools, you have less of that meltwater component, and it becomes more of a sediment starved environment. So kind of like if you looked at a satellite image of the ice margin in Antarctica compared to Greenland, right? Greenland might look really murky because there's more melt, right? More subglacial melt, more sediment delivery versus Antarctica now is a sediment starved margin because of minimal subglacial melt. Still melt. Does that make sense?
Yeah, no, thank you. It's really interesting.
Thanks. Really interesting talk. So we have IPY coming up in the not so distant future now. And just wondering, what are the platform capacities for getting into the continental shelf now that majorities is out?
Yeah, so the Angel system is still around. It's just really expensive. So, like Angel was $30+ million. The Space 2C project, when we budgeted, even just cost to get people down onto the icy plane, it's $5 million, right? But it's not like the difference between the drilling system that we're using, you can only get about 200 meters of sediment, whereas Angel, right, they get like it's more continuous. And we're kind of expecting when we actually are able to drill, to rotary drill, that the recovery might be 60%. So back to kind of these snapshot records, right? But like, I am really motivated, especially after this last year personally. If this system works, it is a tool that can be used for IPY. And if it does work this year, yeah, I think it would be awesome to have more international community effort to use that facility along the traverse in different spots to better understand that underlying stratigraphy, to try to get an Angel type record eventually long term in some of these basins that are just adjacent to the cycle coast. Now, and I know there's efforts by the New Zealanders and the Italians to take this type of system to East Antarctica. And I keep hearing this. We need more Americans to show up to these workshops. And there's a Magellan Plus workshop, I think coming up in June or July, I can't remember. And there's, I can't stress enough how much I keep hearing they want Americans to show up, because the international communities already try to ask these questions, but they want the Americans.
Hi. Yeah, thank you so much for the talk. I was wondering about the M2 event in that Pliocene Delta 18O stack. And I was wondering if there were any hypotheses as to what event caused that.
Yeah, so great question. So there is a hypothesis, and that you get this really nice orbital alignment where you have a node, so minimal tilt and obliquity, and you have a really circular orbit, and it creates these kind of colder, longer seasons that promotes ice growth, and it allows for ice growth to grow and kind of tip the system in a different direction, and provide those positive feedbacks of ice building up over time. Does that make sense? And that hypothesis really stems from, you see this during the Oligocene, during the Miocene, these big periods of ice buildup that are reflected in the oxygen isotope record kind of align with that kind of cold orbital configuration. That makes sense?
Yeah, thank you.
Okay, good. I have a question. I was being polite. There's been a lot of work done on the Ross Sea, right? And we're building up these better and better resolved records of ice margin change and glaciation change there. What other parts of the Antarctic margin do we need to study, and how many areas of the Antarctic margin do we need to study to really fully reconstruct the history of the ice sheet, or do we have a confidence that there are other areas we are already modeled well and we don't need more data?
Sounds like a Lucy question, but I know there's a lot of interest in the Wilkes subglacial basin. This, like, it's kind of the same idea to see how much ice retreated across that basin and Aurora subglacial basin and East Antarctica, because those basins can contribute more than West Antarctica. But, and I think that is super exciting, but I also, you know, the reality is, like, you still don't even know if West Antarctica, how much it deglaciated during the last glacial, right? And ground truthing in that. So I think there's efforts in both regions, and a lot of different regions. I mean, there's so few records. That's because it's just really hard to get to, right, and expensive, and it just takes a long time. Does that answer your question, Chris?
Yeah. Anybody else? Going once? Okay, well, let's thank Molly again for an excellent talk. If you are a graduate student, there'll be a graduate student lunch at noon in the Ice Pod. Thanks to Patty for organizing that. If you are not a graduate student, or if you are a graduate student, we're going to go get beers at 4 o'clock at Austin Beer Works, and everybody's welcome to come to that as well. So, yeah, thank you so much for coming.